So we begin the second topic in our exploration of machine learning, logistic regression. Now I want to emphasize our purpose is not to explore different types of regression. We are using logistic regression to solve a different type of machine learning problem, which is classification. So the emphasis is on methods for classification, and logistic regression as just one example of a method for classification. So here is an outline of the next several lectures. We begin by introducing the classification problem and how logistic regression can be used to solve it. Then we have model evaluation. You may remember we had model evaluation for linear regression as well. You need some method to know how well your algorithm or technique is working to accomplish the task that you want. Part 2 talks about overfitting and underfitting. These are general phenomena in machine learning that apply both to classification and prediction. So we show what the phenomenon is and how to deal with it. Part 3 is practical issues involving with classification. If we break the first part down into more detail, looking at classification with logistic regression, first we come up with model representation. We have to explain where the logistic regression model comes from. Obtaining the decision boundary. Now, making a decision involves setting some kind of dividing line. For instance, price. If something is above a certain price, then you decide not to buy. Or below a certain price, you decide to buy. You have some way of setting a threshold or criteria that decides whether or not you're going to classify the object or sample in a certain way. So how this works in logistic regression, we'll talk about here. Now you may recognize cost function and cost function minimization from linear regression. You need to have some way of evaluating how well your model is working. So you need a cost function, which is like a thermometer or a gauge that tells you how well your model is working. And you want some way of developing a model that has a small cost. The same thing we did with linear regression. We found a way to find linear models that had optimal cost by using gradient descent. Now, accuracy, precision, and recall, and F1 score, these are general concepts that are important in classification, and they are basically different measures for evaluating the classification scheme. They aren't the only ones, but they're the most popular. And we'll talk about the pluses and minuses of all of these different methods. So let's take a look at some practical situations where we're trying to do classification and see how we can develop a model that will enable us to make classification decisions. Here are some example classification problems. Credit riskiness. Someone wants a credit card. You want to know whether or not they're too risky to offer credit to. So you need to make a decision whether or not to offer credit to them. Fraud detection. Someone makes a transaction, a financial transaction. It looks suspicious. You need to decide whether or not this is fraudulent or not fraudulent. Sentiment detection. You have an automatic program to scan movie reviews and the program will scan movie reviews and decide whether or not the review is generally negative or generally positive. That would be a binary classification, 0 or 1. Or you can have a more complicated classification into 3 different schemes: neutral, positive, or negative, 0, 1, or 2. Of course, it's somewhat arbitrary what you assign to 0 and what you assign to 1. Here we said not risky is 0, risky is 1, but we could equally have said that not risky is 1 and risky is 0. Right, so in all of these cases, we're assigning a outcome to individual cases. And that outcome for these cases is either 0 or 1 because we're deciding between 2 classes. And in cases like this where we have more than one class, you would assign different possible outcomes. For instance, facial expression recognition. You have a program that automatically scans photographs and tries to decide what the emotion is being expressed on the face. And there may be several different classes. So the program would assign a number according to the class that it determines. Now, with regression problems, we were trying to draw a line to fit the data as closely as possible. Linear regression used a straight line, but in general, you might use a curve or some other function. With classification problems, you're not trying to draw a line or curve that follows the data, but a curve that separates the data. So I referred previously to the decision boundary. For a 2-class problems, this would be a single separating line or curve that distinguishes between the 2 classes. For a multi-class problem with several different possible assigned labels, you would have a more complicated situation where you might not have just one curve, but several curves. And we'll take pictures of this as we go along. So let's follow up on this idea of decision boundary or separation, line of separation. Let's take in particular the problem of credit riskiness. Suppose we want to determine the riskiness of credit of a particular customer based on the amount of debt that they have. So here we have different customers, and we have their amount of debt. Now, naturally, you expect if the debt is higher, the credit risk is greater. They have a greater risk of not being able to pay back on their loans. And here you can see an assigned credit risk. Now, how was this credit risk determined? Well, it may have been determined by past history. For instance, perhaps this person and this person both defaulted on their loans, or perhaps you have an officer in your organization who determines whether someone is a bad credit risk or not. Right? So these are the assigned credit risks that we're trying to model. Now, in your presentation, you may have this line here. This is not accurate. We're talking about using a single feature to separate the data. So we're creating a separating line based on a single feature. So continuing with the data from the table from the previous slide, we can plot that on a line. If it will let me. All right, so we plotted here the amount of debt of the different people, and then we assign a symbol to whether or not the person was a bad credit risk. And we find that the credit risk was bad for people above this level. Now, in this case, it's quite clear that if I draw a line here that separates the triangles from the circles, then this gives me a good decision boundary that enables me to distinguish between bad and good credit risk. All right, so we predict y equals 1, and then here we predict y equals 0. Now, we would use this same line for future data. We've used past data to determine the decision boundary, and then later we use that same decision boundary to apply to new data. Now, sometimes the determination may be incorrect. It may turn out that someone with a low amount of debt does default on their loan, but we are making a prediction, and predictions will have errors. Okay? Now, let's look in the case where instead of just one feature, you have two features. And really, the same ideas apply. In this case, we have the features of amount of debt and the number of defaults. And then we assign credit risk according perhaps to history, or perhaps some company expert will make this determination. And then we can plot the data. So these are the different data points, and these are the assigned values of y. So in this case, it's quite clear that a separating line is in the middle here, can distinguish between these two. Now, I do want to point out that logistic regression is not finding the equation of this line. The purpose of logistic regression is not to find equations for decision boundaries. Logistic regression does do a line fit, but it's fitting a probability model, not a decision boundary. And again, we'll get more into that later on. All right, so here, naturally, we have predict y equals 1, predict y equals 0, the decision boundary is here. Now, suppose we try to apply linear regression to this problem. In fact, the credit risk is a variable. It takes values 0 and 1. So we could try to predict the value 0 or 1 based on the amount of debt. And we could try to develop a linear model that estimates this value, 0 or 1, based on the amount of debt. So this slide illustrates this. If we add our data here, including the amount of debt and the classification, and we do a line fit, then we could say if the value of h is below a certain value, then we determine y equals 0. And if the value of h is above a certain value, we determine y equal to 1. Again, we only want to make a choice between 0 or 1. So all we need to do is use this line given by the equation h to determine a cutoff point. Right? All right, so here, in this case, the cutoff point might be here. Now, this is a perfectly reasonable scheme. The problem is it just doesn't work very well. When you apply performance measures to this kind of classification scheme, it just performs badly. We can also see, for example, if I add just one data point to this data, then the decision boundary shifts completely. So it's too sensitive to individual data points. So this linear regression approach will not work very well to make a classification. And linear regression just doesn't seem to be the right way to go about this. You're creating a function that ranges from minus infinity to infinity, whereas you're trying to assign numbers that are between 0 and 1. Now, if we think about this classification problem in more detail, ultimately we want to classify each item as 0 or 1. But it might be useful to have a scheme that makes a softer determination, a degree of belief or probability that doesn't just assign 0 or 1 to a data point, but some number between 0 and 1. If the number is close to 0, then that data point is probably down here in the 0 classification. And if the number is close to 1, then the data point is probably in the other class. Now, the advantage to such a scheme is that I can then set my threshold at any point between 0 and 1 and end up with a determination of 0 and 1. But having this preliminary softer determination gives me more leeway. So that's the direction we're headed. Okay, so in order to get there, we'll need a few things. So we need a new hypothesis that can predict in the range of 0 to 1, continuous values between 0 and 1. We'll need a cost function that we can use to evaluate alternative models. The cost function would give large costs if the actual label of an example is 0 while the predicted label is 1, or if the actual label is 1 and the predicted label is 0. In other words, large costs are incurred every time a false prediction is made. Finally, we need a way to determine good models, that is, models that give us low values for the cost function. If you remember in linear regression, we had gradient descent, which enabled us to change the values of theta to get better and better models. So we need something analogous in this case, a gradient descent update that enables us to change theta to get better and better models that reduce the cost function. All right, so let's see if we can construct a function h that takes values between 0 and 1. First of all, we can take some linear function as we had before. Of course, this is not going to be between 0 and 1. And we can write this in matrix vector notation this way as theta transpose times x, where theta and x are both considered as column vectors. Now what we want to do is take a function of this linear expression that takes these restricted values between 0 and 1. Now theta transpose x can take any value along this z-axis here. But what we want is a function h that has an output between 0 and 1. So turns out that this function works well. And there are many theoretical reasons why this particular function is used. There are other alternatives that you could certainly use. You could use some kind of arctangent function, but this one turns out to have a probabilistic justification. So this is the one that's typically used. If you plot this graph, you will see that it passes through 0 and 0.5, and it has an asymptote to the left at 0 and to the right at 1. So that's what it looks like. You can take some specific values to see how this works. So for instance, if z is 100,000, right, you'll plug in 100,000 in the exponent down here. Now e to the minus 100,000 is extremely small. So 1 plus an extremely small number is 1. So you simply get 1 over 1 plus 0, or 1. On the other hand, If z is very small or very large negative, then g to the minus 100,000 is 1 over 1 plus e to the 100,000. E to the 100,000 is an enormous number, so you basically get 1 over an enormous number, which is 0. Right? So you have these expressions, and you can see that this functional form should have this shape. Now, if z is 0, you get 1 over 1 plus 1, which is 1/2, which is 0.5. So this function could be interpreted as a probability. The closer that h is to 1, the more likely the class is 1. The closer that h is 0, the more likely the class is 0. And of course, the values of h are going to depend on the model parameters and the particular feature values for each particular data point. In this way of thinking, we are actually interpreting h as a conditional probability. Now, conditional probability is a hugely important part of machine learning. So it's worth taking a little time to developing the notation of conditional probability. Here we're saying that h is the probability that y equals 1 given the value of x and the value of the parameters theta. So when you see this vertical line, what is to the left is the outcome or determination. What is to the right are the assumed conditions. So this probability is computed under the assumption that these parameters are theta and the value is x. Now, if my feature value is x and my parameters are theta, there are only two possibilities for y. Either y equals 1 or y equals 0. So we can write this equation here. Notice the condition x theta is the same in this term and in this term. So we're saying that under the condition that the features are x and the parameters are theta, the probability that y equals 1 under those conditions, plus the probability that y equals 0 under those conditions, is 1. One or the other of those two outcomes, y equals 0 or y equals 1, must hold. So here we simply rearrange, and we take the first term to the right-hand side, and we can re-express the probability that y equals 0 also in terms of h sub theta. So we always have two ways of saying the same thing. The probability that y equals 1 equals 0.8, that's the same thing as saying the probability that y equals 0 is 0.2. In other words, if someone is a high credit risk, the 80% chance of being high credit risk, that means they're 20% chance of being low credit risk. All right, so we'll finish here and pick up in the next video.